Hi, I'm Rujing and welcome to my midterm progress presentation. My subject is explore different methods to conduct transfer learning for image recognition. Now let me introduce the 5 parts. First, I will introduce background and goals and talk about methodology in 5 experiments. Analyze the experiment, improvements in Project B, and I will make a conclusion. First, I will talk about background. In practice, scientists often encounter situations where there is a lack of sufficient label image data. When there is no available label training data, a challenge appears. The model needs to learn an accurate classifier for new unlabeled image dataset. In machine learning, transfer learning and domain adaptation are two useful methods to cope with this challenge. In this research, we conduct cross-domain transfer experiments from CIFAR-100 to CIFAR-10 so that the model can learn transferable features and solve these domain shift problems. In this research, we observed the performance of different transfer learning models with or without pseudo-labeling. In addition to make a comparison, we also conduct transfer learning in the context of unsupervised learning, semi-supervised learning, and supervised learning. Now let me introduce transfer learning. Transfer learning is using a pre-trained network to predict new dataset. It represents the process of transferring knowledge from source domain to target domain. In general, we use transfer learning in the case that source domain and target domain are different in sample space, label space, and distribution. The main difference between transfer learning and domain adaptation is the change types they cope with. Domain adaptation is a technique to improve performance of a model on a target domain containing insufficient annotated data by using the knowledge learned by the model from another related domain with adequate label data. In this research, we also try to use domain adaptation to solve the domain shift problem that generally solved by transfer learning. In this research, we use CIFAR-100 as source data. Each image belongs to one of 100 classes. We use CIFAR-10 as target dataset, which contains of 60,000 images in 10 classes. CIFAR-100 and CIFAR-10 have different label spaces. In this research, we are supposed to perform image classification on CIFAR-10 and CIFAR-100, so we will mainly focus on transfer learning. In this research, the goal of this research is conduct transfer experiments so that the model can learn transferable features and solve the domain shift from CIFAR-100 to CIFAR-10. And we build different models, observe the performance of different transfer learning models with or without using pseudo labeling. In order to make a comparison, we conduct transfer learning in the context of unsupervised, semi-supervised, and supervised learning. We also try to use domain adaptation to solve the domain shift problem that generally solved by transfer learning. We also introduce a flex match algorithm to improve the performance. Now let me talk about methodology in 5 experiments. We build 5 models. The first 3 models I conduct transfer learning with unsupervised learning, semi-supervised learning, and supervised learning. In the first model, we implement the DANN model, and we try to use domain adaptation to solve the domain shift problem, generally solved by transfer learning. And in the fifth model, we implement a flex match for transfer learning from CIFAR-100 to CIFAR-10 using semi-supervised learning. Now let me introduce the main methodology. First one is pseudo-labeling. As a self-training method, pseudo-labeling tends to choose high-confidence predictions as the base labels. It uses the probability of the unlabeled data as pseudo-labels, so that unlabeled data can be used for model training. The improved consistency loss with pseudo-labeling can be presented as the following function. The below picture shows the illustration of curriculum pseudo-label. The estimated learning effects of each class are decided by the number of unlabeled data samples falling into this class and above the fixed threshold. Now let me introduce transfer learning with SSL. Combining SSL and transfer learning is helpful to achieve better results. As shown in the figure, transfer learning and semi-supervised learning have different functions. SSL utilize the unlabeled target data to improve the generalization of classifier in the target domain, while transfer learning utilizes a large amount of labeled source data to promote the feature learning in the source domain. The two methods promote the learning process from two different directions. Now let me conduct experimental analysis. In Model 1, conduct transfer learning with unsupervised learning without pseudo-labeling. In this research, we build a ResNet 18 model from scratch, training it on CIFOR 100, then use it for transfer learning to predict on CIFOR 10. The baseline of this research is labeled CIFOR 100 data size and unlabeled CIFOR 10 images. We load the pre-trained CIFOR 100 model, replace the final classification layer from CIFOR 100 to 10 classes, then freeze all layers except the final one. Finally, we evaluate on CIFOR 10 test site. The TSNE visualization of CIFOR 10 features is shown in the right figure. In Model 2, we conduct transfer learning with SSL by using pseudo-labeling. The model is first trained on CIFOR 100 to learn general visual features, and we use a small portion of labeled CIFOR 10 data, 5%, and treat the rest as unlabeled. The model generates pseudo-labels for unlabeled data with high confidence. These pseudo-labels are used to train the model further. By using transfer learning and SSL as a combined technique, we achieve a prediction result much higher than the prediction in unsupervised learning. The test accuracy reaches 71.81%. In Model 3, we conduct transfer learning with supervised learning so that we can make a contrast experiment. We use the convolutional layers from pre-trained CIFOR 100 model to build a new CIFOR 10 classifier. We implement a transfer model which will use the previous model's output and learn on top of it. This approach leverages the feature extraction capabilities learned from CIFOR 100 while adding new classification layers for CIFOR 10. The test accuracy on CIFOR 10 dataset is above 92.7%, and the confusion matrix shown in the right figure. In Model 4, we build domain adaptation. Although CIFOR 100 dataset and CIFOR 10 dataset have different label spaces, in this Model 4 research, we try to use domain adaptation to solve the problems that generally solved by transfer learning method. Since the source and target dataset have different label spaces, we need to remap CIFOR 100 labels to match CIFOR 10 categories. By using label remapping, we map CIFOR 100 fine labels to CIFOR 10 categories. And in this research, we use DNN model with feature extractor, label predictor, and domain classifier. We also noticed that CIFOR 100's fine details is discarded during remapping. Even after label remapping, the domain gap persists due to data distribution differences and class granularity mismatch. In the right figure, we can also see that TSNE plot likely shows poor class separation. Now let me talk about improvements in Project B. And in Project B, we introduce pseudo-labeling, fixed match, and flex match. Both fixed match and flex match are sophisticated forms of pseudo-labeling. They all share the same principle. If the model is confident enough, treat the prediction as a true label. Pseudo-labeling is the foundational parent, fixed match is the refined child, and flex match is the smarter adaptive grandchild. Flex match builds on fixed match. It adapts the pseudo-labeling threshold per class based on learning difficulty, fixes the key hyperparameter such as the threshold of the fixed match framework. You can have a look at the algorithm. The flex match algorithm has a main character is determine the flexible threshold. In Model 5, we build flex match algorithm for transfer learning in SSL. The implementation follows the flex match methodology while adapting it for transfer learning from CIFAR 100 to CIFAR 10. The model leverages pre-trained features from CIFAR 100 and fine-tunes using SSL on the target dataset. In this research, we use 5% labeled dataset. Only 5% CIFAR 10 training data is labeled, and the rest of the target data is unlabeled. We conduct pre-training on CIFAR 100, which means we fully supervise training on the source dataset, and then we use pre-trained model except the final layer to adapt it to CIFAR 10. We introduce flex match, and in the SSL, we implement the flex match algorithm with adaptive threshold per class. And in the fifth model, we receive the test accuracy of 43%, and it's only a current test accuracy and will improve the accuracy in the further experiment. Now, let me make a conclusion. By using transfer learning and semi-supervised learning as a combined technique, we achieve a prediction result much higher than prediction in unsupervised learning. Compared with unsupervised transfer learning model 1, semi-supervised transfer learning, with only 5% labeled training data in model 2, can greatly improve the prediction accuracy. And also, in Model 2 and Model 5, we use pseudo-labeling algorithm, such as flex match. It can improve the performance of transfer learning model, help the model to achieve better performance on tasks with limited label data. Now, the below picture is 5 models test accuracy, and we can make a comparison and better understand the performance of different models in different contexts. That's the reference. Okay, that's my presentation, and for any question, welcome to contact with me. Bye.